So when you're looking at this half-life problem, when it says the half-life of zinc dash 71, this is, you don't use this 71. That 71 is just saying that you have a zinc element that has a mass of 71. It's just the mass number, okay? Now get yourself organized with this information. I would get your starting amount, final amount, time elapsed, how much time has gone by, and then your half-life, okay? Our starting amount, they tell us, is 100 grams. So we have 100 G. And then they tell us that the half-life is 2.4 minutes. Okay. And then they ask how many grams we left after 7.2 minutes has elapsed. So how many grams left, that's your X, that's your unknown. And then time elapsed is 7.2 minutes. So once you've gotten your kind of your setup here, then just take a deep breath and try to think through what's happening. They're telling you that you have 7.2 minutes. Every 2.4 minutes, you do a half-life. Remember, a half-life is the time it takes to cut something in half. So every 2.4 minutes, you're going to put your phone away, and then you're going to divide the 100 by 2. Every 2.4 minutes, you divide by 2, and you keep doing that for 7.2 minutes. And they're asking us at the end of 7.2 minutes, how much is left? So what you want to figure out is, what is the number of half-lives we can do in 7.2 minutes? So there's a formula for that. The number of half-lives, number of HF, would equal time elapsed divided by the time for one half-life. So you would do 7.2 minutes divided by 2.4 minutes, and you would get, mathletes? Three, yeah. 3, okay? So then your answer would be 3. We good? No, we're not good. That is not the answer. A lot of people are doing that. They're like, all right, cool, I got 3, so my final amount is 3. 3 is the number of half-lives. That's not right. That's not your answer, okay? So take what you got to do is do the 100 grams, and then we divide it by 3, right? You divide it by, no, that's not what you do. What are we doing here? I'm being too much right now. So what you got to do, the 3, you're not dividing by 3. You're dividing this 100 by 2 3 times. Okay? So let's do that. Do our first division by 2, and you get 50 grams. Do our second half-life, do 50 divided by 2. You get 25 grams. And do one more half-life. 25 divided by 2 is 12.5 grams. So that is your answer. 12.5 grams, that is your final amount. Okay? So everybody, for my own mental health, please put 12.5 down in the formative. Okay? I don't know if I can handle another class where people aren't putting in 12.5 for number 1. You might just start crying. You good? We got that? All right, cool. All right, so let's get your notes out. And let me get my cursor over here. And find ions in atomic spectra. This is the lesson we skipped over, so it's the middle lesson. Find the slide that looks like this. It's got cation and anion. So everybody flip there, and once you're there, start filling in the blanks. Got that? Everybody find it's about the middle of the packet. I would pull up the slide deck on your computer. That way, if I'm going a little too fast for you, you can still keep track. So flip till you get to the ions. Okay. So I told you, like day 1 or day 2, I said, hey, protein protons are positive, electrons are negative. So when you have your basic atom, the number of protons equals the number of electrons. And that's because atoms want to be, they're most stable when the charge is even. So same number of protons, same number of electrons, charge is even. But here's the deal. It's not a perfect world, right? The power goes out, atoms gain electrons, they lose electrons, and they're gonna then receive a charge. If an atom has more protons than electrons, we would call that a cation. If it is an anion, it has more electrons than protons. So here's how this works. We count the number of protons. We got 1, 2, 3, 4. And then the electrons are outside the nucleus. Got 1, 2, 3 electrons. To find the charge I would have 4 minus the 3 electrons. So I would have a positive 1 charge. I have 1 more proton than I do electrons. So that is why we are a cation. Cations are positive. How can you remember that? Well, that T looks like a positive sign. Or cats are positive. If you don't think about it, you know? Anion. Anion's the opposite scenario. Now you have more electrons than protons. So we still have 1, 2, 3, 4 protons, right? But now we have 1, 2, 3, 4, 5 electrons. So if I minus 5, because electrons are negative, you would get a minus 1 charge. So anion, you have more negative charge because you have more electrons. How can you remember that? There's an extra N in anion, N for negative. Yeah.
There's supposed to be like 2 electrons and 1 circle and 8 in the other.
Yeah, you're technically right, but you know, I don't know. Just let it roll. We'll worry about that later. Now, what kind of element would this be? Like if I were to write out the element symbol and I wanted to like have a notation for this, you could do that. What element would this be? You have all the information you need for that. What element would that be? Anybody know?
Which one? Where should I say?
Remember, you determine the element by the number of protons. Yeah, go for it. Be, yep. Be. So if you wanted to write the symbol for this atom here, you would write Be, and then the charge, if there is one, goes in the top right-hand corner. So we said the charge was +1, so you would write +1. Or you could write this as, so you'd see it as +1, or you could see it as just a plus sign, or you could see it as a 1+. If you're like a hipster scientist, it's like, why do I just write the plus after the 1? I don't really care, but you'll see it those 3 ways. Okay? The reason why the plus would work is because it's kind of like an algebra. You don't say 1x, you just say x. The 1 is assumed. Now then, coming over here for the anion version, it's still Be, right? We still have 4 protons. But now you have a -1 charge, so you'd say -1. Or, again, the 1 is assumed, you could just say minus. Or, you know, yeah, if you're just trying to be all cool and stuff, you could say 1- and do that thing. Okay. Everybody still conscious right now? You writing stuff down? Love it. Awesome. Okay, so moving on to the next slide. There can be a scenario where you're not just missing 1 electron or have an extra electron. You could be missing multiple or have multiple extra electrons. In this case, we would adjust the symbol accordingly. For example, if you're missing 2 electrons, you would say +2 or 2+, whichever you prefer. So for example, the second column, Mg2+, that's a magnesium atom that is missing 2 electrons. Okay? Same scenario, you know, same idea with the anions. If you have 2 extra electrons, you would say like S2- or S -2. Notice how you can no longer just say like F-, because the minus only goes with the 1. That makes sense, right? Like here you could say Na plus. You don't need to say the 1. But once you are missing 2 and 3, or you have 2 and 3 extra electrons, you have to include the 2 and the 3. See that? Question so far? Okay. Now then, you're looking at this problem. You're like, that looks like a snagit. I wonder where he snaggited it from. I don't know. Whatever was obj 1c might be from your test. But either way, the question says, which of the following is an ion? So what do we think? B. How'd you know? 1 out of 4 chance. Anybody want to explain? Yeah, go ahead. The protons don't equal the electrons, right? You got 17 protons here, 19 electrons there, right? That's what we call an ion in the biz, right? You got the same number of protons and electrons, that's just an atom. So A, C, and D, they all have the same number of protons plus you as electrons. Okay? Now, if we were to like expand upon this problem, what symbol would I write there? If I want to write the symbol, what would I write? How do you find the element symbol? If I give you the protons, neutrons, and electrons. See them? Remember, it's the protons. Find the number of protons. You got 17 protons. So what's the atomic number of 17? Heard somebody say Cl, yeah? Cl. Now, raising your hand, what charge do I put in the top right corner? Raise your hand. Raise your hand. What would I put? -2. Or again, if you're like some super cool scientist, you could say 2 minus. Whichever you're feeling that day. Okay, not too bad. Okay, cool. Now, there's kind of a lot going on this slide, but a lot of words, but stick with me here. This right here is a picture of an atom. Now, this is the nucleus. Right here, that's the nucleus of the atom. Remember, the nucleus is really, really small. And outside the nucleus, those are the spaces that the electrons occupy. We say that the electrons occupy different energy levels. Where if you are closer to the nucleus, we say you're at a low energy level. So if you're at 1 here, that would be a low energy. And if you're higher up, you're at high energy. That should make sense to you, because if you want to climb a mountain, you need energy to get to the highest part of the mountain. If you're an electron, you want to go from a lower energy level to further away from a nucleus to a higher energy level. You need to gain energy. Now, there's different ways atoms can get that energy, but for us today, who wants to guess how we're going to give these electrons energy? Any guesses? What would be a great way to give these electrons some energy? Light them on fire. You got it. That's where the Bunsen burner is going to come in. So you're going to end up putting these popsicle sticks with the elements in the fire, and the electrons, they're going to start at a low energy level. Let's say they start there. They are then going to travel to some higher energy level. Let's say they go to like 5. Then what goes up must what? Come down, right? So then that electron is going to return to the original energy level. And when it's doing its return journey back, it's then going to give off a color of light. Okay? Now, each element will give off its own unique color of light. Basically, we can use this as like a fingerprint. Get it? Like the idea of the fingerprint, right? If you look at your finger, like the ridges on my finger are different from the ridges on yours. So here, the colors of light that, say, lithium gives off will be different than the colors of light that carbon gives off. So if I want to identify a sample, if I know the color of light that carbon gives off, I can compare it to my unknown color and see which one it lines up with. But again, the whole reason this is happening is the electrons go from a lower energy level to a higher one. Then when they come back to the lower energy level, they give off a color of light. Any questions on that? Alright. And this slide is basically kind of giving you the same thing, but it's but everything I described there, this each element having its own unique color of light, we call that the emission spectrum. So what we're emitting, emission means to emit something, to release something. We are emitting light. Spectrum is like the range of values something can be. So we're emitting different colors of light. And again, that's going to act like a fingerprint. Each element gives off its own unique color of light. So if you look over here at hydrogen, hydrogen's going to give off light here and here. Compare that to helium. Helium, each of these little, like, these lighter shaded bands, that's a band that goes with that specific element. So the combination of colors given off differs depending on the element. Okay? Now, application of this would be like the stars. You know, I don't know if you ever like hear like, oh, this star has such and such gas in its atmosphere. You know, how in the world could they even know that? That feels made up. They're saying some star like, you know, however many light years away just has this kind of gas in their atmosphere. Well, what they do is they have telescopes that can receive that electromagnetic radiation, that color of light, and analyze it and see, okay, if we got this and this color of light from this star, it must have oxygen in its atmosphere. We got another different colors of light coming in, that lines up with neon. So that's how they can get an idea of the different gases that make up the stars. Which I think is kind of neat. Okay. Okay, shifting gears a little bit. This is getting into the, this is really a review. At the very end of the formative you're doing today, I have a chart for you kind of like this, where you're going to fill in, you know, I give you an element, different numbers of neutrons and protons, and you fill in the missing ones. So reminder on this chart that the atomic number equals the number of protons. Those are the same. The mass number is going to equal protons plus neutrons. That plus that will equal the mass number. Okay? Maybe I can put a little plus sign there if that's helpful. Okay? Let's run through some examples, and I think you'll kind of see where we're at with this. So calcium has an atomic number of 20. So that tells us that calcium has 20 protons. Now, mass number. You're like, well, where would I get that from? You would not look at the periodic table. You look at the mass number notation, where the number after the dash, this is not minus 40, this is dash 40. That 40 there, that's the mass number. Okay. Get a sip of water. I don't think I've ever been so hot teaching. Like, it's just, it's a lot going on here. Okay, I'm going to make everybody, I'll power through. Now then, to find the number of neutrons, you have a 40 for the mass number. 20 plus what equals 40? 20. Okay? And then they filled everything else for us. If we go to the third row, got sulfur. Sulfur, 16 neutrons, atomic number is 16. If the atomic number is 16, that's the number of protons. So we're going to put 16 there. Then the mass number. Everybody still following along? We still writing? I'm putting you to sleep. I wouldn't blame you, you know. Happens. I put my wife to sleep all the time. We're just like talking, and she just like falls asleep. I'm just kidding. How sad would that be? Just like
I'm with you on that, man.
She's like, "Are you still talking right now?" Like, she's like, got a full nap in while you did that story. Okay, so then for the isotope notation, you would put S. Then in the top left corner, that's the mass number. We're familiar with that notation. We've done that with like the nuclear decay stuff. So they tell us 32 is our mass, so 32 goes up there. Smaller bottom left number, that's the atomic number. Yeah, good, that'd be 16. Okay? And then for lithium, atomic number is 3. So number of protons is 3. All right? Then mass number notation, right? Li dash, then put the mass number. So mass number is 7, put a 7 there. And then for isotope notation, remember isotope, same element, different numbers of neutrons. Okay? So here, Li Mass goes top left, so Li 7. And then 3 is going to go in the bottom left. Almost done. Here, atomic number 8, so that's why protons is 8. Mass number, geez, where would I get that from? Anybody raise your hand, help me out here. Where would I get that mass number from? You got it? Sorry, a little louder.
Then you add them together.
Oh, do not add them together. You would not add these two together because the atomic number is number of protons. The mass number is neutrons plus protons. So the issue here is we don't know this or this, so how would we find it? Yeah, go for it. Yeah, you. I don't want to say your name. Yeah.
Sorry. So I could find it from the isotope notations. It says the mass on the top left.
Top left, there you go. Yeah, so 16 there, so mass number is 16. So 8 plus what equals 16? That would be 8. Okay? All right, now then mass number notation. We good there? I think I heard somebody say where you get 16. The 16 is coming from this number in the top left. That's the mass number. Okay? All right, then you're going to put O dash mass number, 16. Okay? I'll let you finish writing that, and then I'm going to start explaining the lab. Let me stop recording. No?